Section 1 Introduction. We're going to delve into the world of large multimodal models, LMMs, particularly visual language models, VLMs, which are gaining traction in the development of general-purpose assistants. These models are impressive because they can both perceive and reason. However, it's been a challenge to link the representations of pre-trained large language models, LLMs, and vision models to reveal cross-modality properties, such as visual question answering, image captioning, and visual knowledge reasoning. Some models, like GPT-4 and Gemini, have shown remarkable performance in these tasks, but unfortunately, there's not much technical information available about them. Meanwhile, the research community has proposed several language tuning methods. For example, Flamingo uses visual tokens to condition the frozen language model through gated cross-attention layers. Blip2, on the other hand, believes this interaction isn't enough and introduces a lightweight querying transformer, QFormer, that extracts useful features from the frozen vision encoder and feeds them directly into the frozen LLM. There are also models like MiniGPT-4 and LLAVA that use different strategies to align a frozen visual encoder with a frozen language model. Training strategies are also evolving to accommodate large-scale multimodal data. For instance, LLAVA is one of the first attempts to apply the instruction tuning paradigm from LLMs to multimodal scenarios. Despite these advancements, there's a growing need to enable cross-modality capacities in resource-constrained scenarios. Gemini, for example, has surpassed state-of-the-art performance on a range of multimodal benchmarks and introduced mobile-scale VLMs with 1.8 billion and 3.25 billion parameters for low-memory devices. Our goal is to build the first open, mobile-scale VLMs trained using public datasets and available techniques to achieve visual perception and reasoning, customized for resource-constrained platforms. We're proud to present MobileVLM, a full-stack remake of multimodal visual language models tailored for mobile scenarios. We believe we're the first to provide a detailed, reproducible, and strong vision language model from scratch. We've conducted extensive studies on the design of visual encoders and evaluated the VLM performance sensitivity on various training paradigms, input resolutions, and model sizes. We've also designed an efficient projector between visual and text features, which better aligns multimodal features while reducing the inference budget. Our model is designed to run efficiently on mobile, low-power devices, with a measured speed of 21.5 tokens per second on a Qualcomm mobile CPU and 65.3 tokens per second on a Justin Orin GPU. Our models perform comparably on a large body of VLM benchmarks, attesting their potential in numerous tasks in practice. In terms of related work, the vision transformer is now the dominant backbone for visual perception. Its successors, such as SWIN, DAIT, PVT, and TWINS, have upgraded its original architectural design to strengthen its representational power and efficiency. Large language models often come with billions of parameters and are pre-trained on extremely extensive text corpora, exhibiting emergent capabilities that have not been witnessed before. They have reshaped the field of natural language processing and are being used in a wide range of applications. There is a trend to build smaller language models, with parameters around 1 billion or fewer. Examples include GPT-Neo, Pythia, OpenLLAMA, Phi, and Qwen. Although privately collected high-quality data can significantly boost the performance of LLMs, our target is to build reproducible and efficient models, hence we do not utilize any non-public data for our research. Section Summary. Large multimodal models, LMMs, such as visual language models, VLMs, have shown great potential for building general-purpose assistants due to their improved perception and reasoning capabilities. However, connecting the representations of pre-trained language models and vision models to uncover cross-modality properties has been challenging. In this paper, the authors present MobileVLM, an open and mobile-scale VLM tailored for resource-constrained platforms, and conduct extensive studies on visual encoders, training paradigms, and model sizes to optimize performance. Their model achieves high performance on various benchmarks and outperforms many recent VLMs, even on low-power devices. Section 2.3 VLMs. In recent years, we've seen a surge in the development of vision language models, VLMs. These models are compared in detail in a table, focusing on their architecture, cross-modality design, and training data. When it comes to architecture, due to the high training costs of large language models, most VLMs use pre-trained open-source models such as Opt, Flan T5, Chinchilla, Vicuña, and Llama. Qwen, for example, modifies Llama to create their own language model. The visual components of VLMs are usually vision transformers, trained in various ways. Most VLMs favor a clip-style VIT trained with natural language supervision. Flamingo, however, opts for NFNet F6, while Cosmos chooses VLMO. The creation of training data is becoming increasingly important. It's common to use millions of text-image pairs in VLMs, with new datasets often released alongside their corresponding new models. For instance, the multilingual multimodal model Qwen-LM not only has an improved visual receptor and language model, but it also aligns the image with caption and box tuples, setting a new standard for generalist models. Poly and PolyX use an internal multi-language image text dataset called WebLI, which contains 12 billion entries. Recently, shared GPT-4 volts has been used to generate 1.2 million high-quality image text pairs to overcome the limitations of current image text datasets, such as hallucination and inaccurate descriptions. This has led to significant improvements in the LLAVA series. Similarly, LVISINSTRUCT4V, also built with GPT-4V, has helped LLAVA 1.5 to perform better on various VLM benchmarks. Large language models, LLMs, have revolutionized natural language processing. However, their size and computational demands pose significant challenges, especially in environments with limited resources. These models often require a lot of memory and processing power, and their energy requirements raise sustainability concerns. To address these issues, researchers are focusing on model compression, which aims to reduce the size and computational demands of models without significantly compromising their performance. Techniques include model pruning, quantization, knowledge distillation, and low-rank decomposition. Evaluating different VLMs is crucial. Pope, for example, provides a benchmark for evaluating hallucination in VLMs. GQA focuses on the VLM's abilities in real-world reasoning, scene understanding, and compositional question answering. Text VQA evaluates models' OCR and reasoning abilities by asking questions related to text in the image. Science QA consists of multimodal multiple-choice questions covering scientific topics, requiring VLMs to integrate common sense into reasoning. Our work is closely related to embodied artificial intelligence, a field that aims to build intelligent systems that can interact with their surroundings. Recently, large vision language models have allowed embodied AI agents to solve tasks like embodied question answering and vision language navigation in a highly end-to-end fashion. With the goal of achieving efficient visual perception and reasoning for resource-limited edge devices, we designed the architecture of MobileVLM. It consists of three components: a visual encoder, a tailored LLM for edge devices, MobileVLM, and an efficient projector, termed lightweight downsample projector, LDP, that aligns the visual and the textual space. The vision encoder takes an image as input and extracts the visual embeddings for image perception. To address efficiency issues arising from prolonged image tokens, we use a lightweight projector for visual feature compression and visual text modal alignment. This converts the visual features into the word embedding space with an appropriate input dimension for the subsequent language model. We then obtain the image tokens and text tokens, where the number of text tokens and the hidden size of the word embedding space are denoted by ent and dt respectively. Given that LLMs consume most of the computation and memory in the current design paradigm of MLLMs, we tailor a series of inference-friendly LLMs that are faster for mobile applications. These predict the response conditioned on the multimodal input in an autoregressive manner, where L denotes the output token length. Section Summary. A comparison of various vision language models, VLMs, is provided, highlighting their architecture choices, dataset-centricness, model compression techniques, VLM benchmarks, and their relation to embodied AI. Model compression techniques such as pruning, quantization, knowledge distillation, and low-rank decomposition are used to reduce the size and computational demands of large language models, LLMs. The overall architecture of MobileVLM is designed with a visual encoder, a tailored LLM for edge devices, MobileVLM, and an efficient projector for visual text alignment. Section 3.2 Visual Encoder. We've chosen to use a pre-trained MobileVLM model as our visual encoder, which we'll refer to as F_ENC. This model breaks down images into uniform-sized patches, applies a linear embedding to each, and adds positional encodings before feeding the resulting vector sequence into a transformer encoder. Usually, a classification token is added to this sequence for subsequent categorization tasks. For the language model, we've scaled down Llama to make it easier to deploy. This means our models can be supported by almost all popular inference frameworks. We also assess the model latency on edge devices to guide the model design. We're considering using a neural architecture search in the future, but for now, we're sticking with our current design. We use the sentence piece tokenizer from Llama 2 with a vocabulary size of 32,000 and train the embeddings from scratch. This will make future distillation easier. The context length used at the pre-training stage is 2K for all models due to limited resources. However, the context window can be scaled up to 8K for inference. The projector between the vision encoder and the language model is crucial for aligning multimodal features. There are two existing paradigms, Q-former and MLP projection. Q-former controls the number of visual tokens per query to extract the most relevant visual information. However, it loses the spatial positional information of tokens and suffers from slow convergence. It's also inefficient for inference on edge devices. On the other hand, MLP retains the spatial information but often includes unnecessary tokens such as the background. For an image of x_v in R to the power of h times w times c with a patch size of p, there are n_verses equals hw divided by p squared visual tokens to be injected into the LLM model, which significantly slows down the overall inference speed. To enhance the positional information and encourage local interaction of the vision encoder, we use convolutions. Specifically, we explore mobile-friendly operations based on depth-wise convolution, which is efficient and well supported by various edge devices. To keep spatial information and to minimize the computational cost, we use a convolution with a stride of 2, which reduces 75% visual tokens. This design significantly boosts the overall inference speed. Our training process consists of 3 stages. First, we pre-train LLM foundation models on the text-only dataset Red Pajama v1. Then, we perform supervised fine-tuning on a dataset of multi-turn dialogues between humans and from third-party platforms. Finally, we train our vision large models using multimodal datasets. For language model pre-training, we train all the models on 1.3 trillion tokens from the Red Pajama v1 dataset only. We use a global batch size of 5,242,880. The peak learning rate is set to 0.0003 and it decays to 0.00003 following the cosine strategy. We warm up with 2,000 iterations. We use the Atom W optimizer with beta_1 equals 0.9 and beta_2 equals 0.95 and a weight decay regularization value of 0.1. The gradient clipping threshold is set to 1.0. For supervised fine-tuning on language models, we use a dataset of multi-turn dialogues between humans and from third-party platforms which has been cleaned through a process of format standardization and quality refinement. We fine-tune for 3 epochs with a learning rate of 0.0002 for MobileVLM A1.4b, and 2 epochs with a learning rate of 0.00003 for MobileVLM A2.7b. For vision large model training, the whole training process comprises 2 steps, pre-training and instruction tuning. During the first step, we freeze the vision encoder and LLM, focusing on training the efficient projector only. Then, we fine-tune both the projector and LLM to enhance the abilities of visual understanding and expression by refining the language model via language modeling loss function. We pre-train our model on the filtered CC595K subset for 1 epoch at a learning rate of 0.001 and a batch size of 256. We fine-tune it on the LLAVA instruct 158K dataset for 1 epoch at a learning rate of 0.00002 and a batch size of 128. The training takes 5 hours with 8 NVIDIA Tesla A100 GPS for MobileVLM 1.7b, and 8 hours for MobileVLM 3b. Section Summary. The visual encoder used in this work is a pre-trained MobileVLM model, which dissects images into patches, applies linear embeddings and positional encodings, and then feeds them into a transformer encoder. The language model is downscaled for deployment and uses a sentence piece tokenizer with a vocabulary size of 32,000. The efficient projector between the visual encoder and language model utilizes depth-wise convolutions to enhance positional information and reduce computational cost, resulting in faster inference speed. The training process consists of pre-training the language model on a text-only dataset, supervised fine-tuning on dialogues, and training the vision large models using multimodal datasets. Section 4.2 Evaluation of MobileVLM. In Section 4.2, we evaluate our MobileVLM models using two standard benchmarks for language understanding and common sense reasoning. We use the Language Model Evaluation Harness tool for the first evaluation. Our results show that our MobileVLM 1.4b model performs as well as the latest open-source models, such as TinyLLAM 1.1b, Galactica 1.3b, Opt 1.3b, and Pythia 1.4b. Interestingly, our MobileVLM 1.4b model performs better than the TinyLLAM 1.1b model, even though the latter was trained on twice as many tokens. At the 3 billion token level, our MobileVLM 2.7b model shows competitive performance to Insight 3b, v1, and OpenLLAM 3b, v1, and is about 40% faster than OpenLLAM 3b on a Snapdragon 888 CPU. For common sense reasoning, we report the zero-shot accuracy on 5 popular benchmarks. Our models show strong reasoning capabilities on these benchmarks, with MobileVLM 1.4b and 2.7b achieving the highest performance on the Winagrande benchmark at both 1 billion and 3 billion token levels. This suggests that our models have robust common sense capabilities and do not rely on systematic biases in the datasets. We also evaluate our models on several language understanding tasks, including PIQA, HelloSwag, and MMLU. Our MobileVLM outperforms other models across nearly all of the benchmarks, making it more suitable for downstream tasks, such as instruction tuning and in-context learning. In Section 4.3, we evaluate the multimodal performance of our MobileVLM model on several benchmarks, including GQA, ScienceQA, TextVQA, POPE, and ME. Despite having fewer parameters and limited training data, our MobileVLM model performs competitively and even outperforms some of the previous state-of-the-art multimodal vision language models. However, the lack of large training datasets, such as code and textbooks, results in a noticeable performance gap on tasks like ScienceQA and ME. In Section 4.4, we investigate the use of low-rank adaptation, LoRa, on our MobileVLM model. During the visual instruction tuning stage, we freeze all the language model parameters except the LoRa matrices. The updated parameters are only 8.87% and 7.41% of the full language model for MobileVLM 1.4b and MobileVLM 2.7b respectively. Our results show that MobileVLM with LoRa performs comparably to full fine-tuning on 6 benchmarks. In Section 4.5, we measure the inference latency of MobileVLM and MobileVLM on a Realme GT mobile phone and an NVIDIA Jetson AGX Orin platform. Our MobileVLM 2.7b model significantly outperforms OpenLLAM 3b at the same quantization precision on the Snapdragon 888 Society. Notably, MobileVLM 2.7b achieves twice the inference speed of OpenLLAM 3b, while using 2/3 of the RAM and half the loading time. For the smaller model, although the quantized MobileVLM 1.4b is 23% larger than TinyLLAM 1b, its inference speed is only 11% slower, showing the benefits of our model's better architectural design. On the Orin platform, MobileVLM is quite competitive to the open-source language models at similar parameter scales. Due to the limitation of the llama.cpp framework, VLMs are split into the vision encoder and the language model, which are loaded separately during the inference stage. The prompts of VLMs are composed of textual prompts and visual prompts. For a fair comparison, LLAVAV 1.5 and MobileVLMs take the picture with the same resolution of 336 by 336 as the visual prompt, along with the sentence, "What is in the picture?" as the textual prompt. The total inference time of VLMs is calculated specifically as the sum of the time to load the language model, the time to process the input tokens, the time to generate all response tokens, and other negligible overheads. Our results show that MobileVLM equipped with MobileVLM A2.7b and MobileVLM A1.4b consistently outperforms LLAV AV1.5 on both the Snapdragon SoC and Jetson Orin platforms. This proves the importance of efficient projection that reduces the number of input visual tokens. Section Summary. In the evaluation of MobileVLM, the models demonstrate competitive performance on language understanding and common sense reasoning benchmarks, outperforming other models in many cases. MobileVLM also achieves competitive performance on multimodal benchmarks, although there is room for improvement in tasks that require large training datasets. Additionally, MobileVLM with low-rank adaptation, LoRa, achieves comparable performance to fully fine-tuned models with fewer trainable parameters. The inference latency of MobileVLM and MobileVLM is evaluated on mobile devices, showing that MobileVLM outperforms OpenLLAMA in terms of speed and efficiency, while MobileVLM achieves faster total inference time compared to LLAV AV1.5. Section 5.1 Ablation on Vision Backbones. In this section, we'll discuss the effects of various factors on the performance of our multimodal model. We'll look at the impact of model scale, the number of visual tokens, and pre-training paradigms. We'll also examine the role of vision language projectors, visual resolution, token numbers, and the influence of specific fine-tuning methods. Firstly, we found that as we increased the size of the model, the performance across 6 benchmarks also improved, given the same projector. However, there seems to be a limit to this improvement, as the benefits of scaling the visual model start to plateau after a certain amount of training data. Secondly, we discovered that reducing the number of visual tokens by 75%, from 576 to 144, using our proposed LDP module didn't negatively impact performance. In fact, sometimes it even improved it. This suggests that the quality of visual tokens can be enhanced while still maintaining the effectiveness of our LDP module. Thirdly, we evaluated the performance of our model under different pre-training paradigms. We found that the performance improved as the cost of pre-training increased. The best results were achieved when the vision encoder was pre-trained with supervised image text alignment. Interestingly, we found that models pre-trained by grounding detection performed comparably to those pre-trained using the clip method on several benchmarks. This suggests that aligning at the image level could potentially yield better results than object-level alignment, especially when using more visual tokens or more training data. Next, we looked at the impact of vision language projectors. We found that both feature interaction and token interaction were beneficial. We used depth-wise convolutions for feature interaction and point-wise for token interaction. We found that adding more parameters didn't necessarily lead to better results. However, downsampling tokens at the end of the projector did have a positive effect. We also examined the effect of visual resolution and token numbers. We compared 2 strategies, reducing the input resolution and using a lightweight downsample projector. We found that the latter strategy was more effective. Finally, we conducted a quantitative analysis on the effect of specific fine-tuning methods. We compared 2 common methods, Alpaca and Vicuña, and found that the latter, when used in dialogue mode with data from shared GPT, significantly improved the scores on several benchmarks. We also found that integrating the prompt format of the fine-tuning method with the training of downstream tasks improved performance.